we'll move on to the next talk. It will be presented by Dr. Donglai Dai. He's a chief engineer at X-ScaleSolutions, where he leads the company's R&D team. His current work focuses on developing and enhancing communication libraries, checkpointing libraries, secure communication libraries, and performance analysis tools. He's the principal investigator of several DOE SBIR grants and member of the PC committee for SuperCheck SC23 workshop. Before joining X-ScaleSolutions, he worked at Intel, Cray, and SGI. He holds over 10 US patents and also has published 40 technical papers, presentations, or book chapters. He actually is a graduate from the Ohio State University. So today you'll be talking about accelerating HPC and AI application using various packages from X-ScaleSolutions. So let's give a big welcome to Donglai.
I sent to Kaushik. I sent on Monday. Hello. Okay, we're on. Okay. This talk is going to cover a few of our major products. Okay, and specifically, all these products are for accelerating applications in HPC application or AI applications. And since I give the tutorial on Monday, so some of the product I will just highlight something, and I'll focus on the ones I did not touch on Monday. Okay, so this is the outline. I will briefly discuss our company, then I'll cover each of the 4 major products. Okay. And so as you, X-ScaleSolutions itself was founded. Well, it's actually started operations in 2018. So now we have been in business for more than 6 years. And so the emphasis is we give efficient end-to-end solutions. It's just a moment. End-to-end solutions for services, solutions as well as services, and supporting the training. And we are specifically focused on communication in parallel and distributed computing related stuff. Okay. And for all our product, we emphasize we can do platform-specific optimization and tuning, as well as application-specific optimization and tuning. And we give best practice for our products based on whatever your architectural system, including system software as well as hardware architecture, the best practice to get the best result. And we also, since we also provide a commercial support, and depend on what level of contract level you ask for support, we give a different guarantees, like how long it takes to resolve the issue, or at least response to your issues, okay? And also based on our contract, if you reach certain level, we actually give all the update free if your contract is valid during that year. Okay. And we has a portal-based service issue filing, and you can track each of the issue with, in your regard, whatever you have, track its progress and the status. And so that is the main thing as far as the company's service and product is concerned. As ourselves, we're a winner of multiple DOE Small Business Innovation and Research Grant. And we market, like we mentioned at the beginning, the communication-focused packages for software, for HPC as well as AI. Next, I'm going to cover each of the major products currently we have. Well, by the way, we actually have 5 more, a few more than this, and another one is HPC for focused on HPC only. Okay, but I'm not going to cover that part. So I'll start with the MVAPICH2 DPU package. This package basically is, in overall, is doing offloading some of the communication-related functions into the DPU unit, the NVIDIA. Okay, the design is general enough that we could potentially migrate it and support other DPUs as well as IPU from Intel, things like that. And so we create a novel framework to offloading non-blocking collectives. Okay, we emphasize the non-blocking because that gives us the best opportunities to do the offloading so that it can operating in an overlap fashion with a computation where you potentially use the GPU, CPU or GPU, depends on whatever you use, to allow the DPU doing the communication related stuff. Okay, and currently we're able to, the library we provided it to able to offloading all-to-all, as well as broadcast and all-to-all V all gather, as well as point-to-point blocking and non-blocking. But we emphasize non-blocking here as well. Okay. To all this functionality related to communication to DPU. And this is showing how effective the offloading is. We are able to achieve that close to 100. Most time it's high 90s, but for the extremely good ones, we are able to achieve 100% overlapping. Means the CPU is just initiate its communication, whatever needs to be offloaded to the DPU, then it can go on to the next piece of computation it needs to be done. And the communication will happen at the meantime. And then once it's at the appropriate later time, you can check whether the communication need to happen has been completed or not. Okay. And as you can see, this one, for small messages, we are achieving typically in the high 90s, especially for the collectives. And this is very typical. Okay. And for point-to-point, because the communication normally takes a less amount of time. So that depends on how many outstanding requests the application is needed, then that will determine how much of a operation the communication can be overlapped with your computation. And this is a cross-port. So for larger messages, this is even more efficient. And this one particular one, we're showing Okay, this is one of the application kernels we are able to achieve. So this is FFT, which actually, I think in this conference, we talked about specific ones, HE FFT, which is based on the GPU. And this one, we're showing something based on the CPU only, okay? And as you can see here, for this particular application, it's P3D FFT, that version. And for most of the different application sizes, this is problem sizes. Okay, as you can see, we're also this is 3D, 1K, each dimension. And this is each time we double it, okay? And so the problem sizes are getting bigger and bigger. And our efficiency actually is quite stable. It's around around 15%, sometimes higher, sometimes lower, depends on your application behavior itself. And for this actually is for even larger, more cores you use, we're achieving better, even higher overlap because the memory as well as cores are busy doing useful computations. The communication can take its time to finish. And this is understand at the lower level, basically, this is another application kernel. It's a PETSc, okay? And we're looking at, this is using offloading point-to-point, doing and reduction using PETSc. And as you can see here, we are able to achieve basically about between 20 and 25% for most of the time. And by the way, this is using point-to-point as well as a reduction. And we're saying this particular one is showing strong scaling because we're fixing the problem sizes for this. In the end, it's tail off because we have less computation you can do. Okay. And this one is for the X-ScaleAI, which actually is for the HPL. This is a high performance benchmark used to rank the 500 list. Okay, and even for this actually benchmark is famous for its scaling, and communication is supposed to be a relatively low proportion of the overall execution. Okay. But even for this, because it's user broadcast, okay, even for this, we are, as you can see, we can improve the performance by around 10% or, between 10 or 15% or something like that. And this actually, when we present this result in some other conferences, and people are quite impressed by this because broadcast or communication normally does not make a significant difference, but we're even for this, because our efficiency in overlapping, we're able to achieve this. And this one is for the third application. Okay, it's called X-Compact 3D. This is a fourth, I should say, for the application. So this is incompressive. It's used for flow dynamics or that type of application. And this is a kernel for that. And we're running this one on AMD system. And as you can see, this is similarly, we can achieve between 10% or 15% based on different problem sizes. Okay. And this one is use 8 AMD nodes. I believe it's, what's the PPI here? We did not show the PPI. Oh, PPI is 128. So total is 1 kilo ranks. Okay. So this is a decent size for decent problem size as well as a decent system size. So 1 kilo ranks. Okay, that's for the offloading effective for the HPC application. Okay, and then the next one I'll touch on the secure MPI package. Currently, we're working on, and the release will come. The very first release will come within a few weeks. So the overall goal is provide a scalable solution of the secure communication for HPC applications. And this is based on the OSU, again, based on OSU's MVAPICH libraries. And our major feature is it's going to be supporting, provide flexible support for multiple cryptographic libraries, as well as different encryption schemes. Because what different applications on the environment, they may ask for different level of protection. And for different level of protection, that means the schemes you use sometimes is more complicated than others. So we want to give people the choice of choosing the right balance for their particular environment. Okay, and also this gives us a universal plug-in interface for future extension. If some of you ask me questions, I can explain that. Okay, and then we one of the key is how to you manage the security key distribution and keep that as a secret during your computation. And we actually, in the library, we followed the current industry standard. It's a TLS, basically a transportation layer security, as well as SSL, okay? That key management for the session of the entire computation for your application, okay? And we do have some mechanism potential put in if you think your application itself running for days or weeks or something like that. We can even configure the type of, how long you think it's secure for your application. Then you can switch to start a different session. And here we actually support secure point-to-point blocking and as well as non-blocking, and as well as some of the collectives. Okay, we will show. We are working on supporting more collectives, and right now for the first release we will support 4 different collectives secured. And we work hard to make sure the installation as well as execution command as simple as possible, so that people don't feel like they need a lot of pre-setup to run this, especially for running. Setup, if we set it up properly for once, then you don't have to do that again. And we support, last will be, it has been tested using micro-benchmarks as well as applications up to 1 kilo ranks. And of course, if we have more time as well as resource, we want to test this with bigger scales. So more information has been presented on Monday's tutorial. You can take some information there if you want to, or you can ask questions or contact us for more detailed information. Okay, the next few slides, I will just show some of the highlights. And this is using blocking point-to-point and use a micro-benchmark, OSU benchmark. It's a OSU latency micro-benchmark. I just emphasize a few things. First, this figure showing the orange one showing unencrypted, no secure protection, okay? And the purple one showing the naive ones. Basically, you encrypt your message before you send. Then after you receive it, you decrypt it at the receiving end. This is something very similar to IPsec in the standard, in IPsec standard. Okay. And then we're showing the blue ones are the ones we put a lot of optimization mechanism in, and that's what our current library are able to achieve. And as you can see, and this one is on Intel processor, and since we're supporting either boring crypto language library as well as Intel, so those ones are interchangeable, and performance are similar. We put on this one because some systems support Intel crypto language because they have some trade-off between the two, okay? And others prefer a boring SSL. So as you can see here, especially for large messages, we are able to cut down the protection or security overhead significantly from more than 7 times slower to about 17%, not 17% slow. Okay, so that's very significant. And for smaller ones, you can see that may be slightly small, but still it's very noticeable. So you get the protection, but still you are only paying as a little bit more overhead because of the protection for the performance impact. And by the way, that's what we are saying is this package is providing the security protection with minimum performance overhead. Okay, so this is just one. This is blocking point-to-point. And this is blocking all-to-all. So this is one of the most popular collective operations. And again, as you can see here with the three groups, and so if you compare the naive sometimes you get a 1.5 times slower, okay, around that. And we are mostly within a single-digit performance percentage overhead, okay? So still significant reduction. So you're talking about 50% less to about 5 or 6% overhead. And this one is showing 512 core ranks, okay? And we're running this one on 16 nodes, 32 ppm. That's total is 512. And this one is again showing one of the application kernel, which is P3D-FFT, again on the CPU only ones. And as you can see, whatever we're showing on the micro benchmark, actually the end application get benefit from. And here, application actually showing, because this is using all-to-all, okay? So for the particular package problem sizes, this benefit changed somewhat because of the characteristics of your communication as well as your computation is changing based on your input as well as, input problem sizes as well as your computation grid. And this is showing the same number of nodes with a different number of ppms, so your total ranks are changing. And as you can see, we are still seeing noticeable benefit, okay? And maybe 2.5x or 2.6x, and sometimes it's more than that. Okay, now move on to the third one. It's a X-ScalePETSc. This is an optimized PETSc library, because the PETSc is open source. It's a non-linear numerical library for partial differential equations and things like that, okay? And we're co-designed this with MVAPICH-based MPI so that the two can be better, can work better for performance benefits. And so the first release has been achieved in April of this year. And if some of you are interested, definitely contact us for a license. Or we can give you a free trial license, okay? And so again, this is potentially we're saying that we particularly optimize for small to medium message intra-node communication, basically CPU to CPU. And for one thing is we use a matrix multiplication things to make sure that the optimization actually get benefit showing for the end application. And there's many different what is called the solver in this library, okay? And we find this matrix this particular one, matrix MPIAID. Those are particular name of that solver, okay? That's one of the solvers used most popular in the matrix multiplication. And that particular one and its subclass, we are able to optimize, co-design that part and show some benefit, we can show that, okay? And so the overall, we're focusing on intra-node as well as inter-node. So basically within a node as well as across node communication for this particular one. And as far as the user is concerned, and the end application is concerned, there's no difference when you call the PETSc library itself. Okay, so the PETSc API remains the same. It's just the supporting part inside that one we optimize. And so the next few, I think 3 slides, will show some examples what we are able to achieve. I mentioned the matrix multiplication, but matrix multiplication is using matrix vector as one of the variations. So here is using matrix vector solver, okay, multiplication solver, and there is one more. This is how the PETSc library itself designed their structure, because this one is used in DMDA. Okay, if some of you use that, you will know what that means. It's basically for distributing the global matrix and local matrix, how you manage the mapping relationship. And this one, particular one, we're using stencil and using width of 5, basically is your neighbors, okay? And so you take your 4 neighbors and doing average on that, okay? And but the width is 5. What does that mean? Is 5 deep. For your 4 neighbors, you are not only take 1 neighbor element, you take 5 deep, okay? So that has a quality on your reach to conclusion is faster, supposedly to improve your overall accuracy of your solution. And so this one particular one we can see is on either it's 4 nodes or 16 nodes. We are able to achieving 13%. I mean, the percentage will change somewhat, okay? Depends on how you map them and how many nodes you use. But the benefit is sustainable. It's between 10 to 15%, at least for the things we have tested on the architectures we're testing. Okay. Oh, here, this was tested. The result is obtained on Frontera. We actually tested on HP Kaga and other things as well. Okay, but this particular result is achieved on Frontera. And this one is for Python. Python problem is also part of the library. It's a different application suite. And it's actually a different solver. And we did the similar thing. We co-designed this solver with MVAPICH library, and we optimized, tried to use appropriate overlap scheme as well as appropriate protocol and parameters, all that type of thing. And this one, as you can see, for 2 nodes, 4 nodes, 8 nodes, 16 nodes, the ranks start from about 100 all the way to a close 1K. Okay. And as you can see, it's about 8 to 10% for this solver with that problem sizes. Okay. And I think this is, yeah, another application kernel. This is another just the solver. This is application that use some of the solvers, okay? And we optimize this, and this is able to see, this is actually is a Laplacian, using Laplacian solver, okay? And as you can see here, by the way, the pattern is a 3D Laplacian, and it's use a Cartesian structured mesh. So it's a 3D, okay? And the neighbor, if you count it, 3D, you have 6 neighbors, okay? And plus yourself. Now this is deep-wise, I think it's, did not show, right? You can calculate this. If you times 6, it's 4 deep, okay? And again, we are able to see for this particular ones, it's about 8%. Okay. And in the last one, this is showing portability, basically across different systems. And yeah, the one of them showing Poisson, the other one showing stencil. Okay, so this benefit is you across different architecture as well as different solvers that could be achieved. Is that right? Okay, now I'll move on to the last one. This one is for X-ScaleAI package. And by the way, I covered this part on Monday, so some of the details can be checked out there. And this is about this particular package. Again, following our general guidelines for the company, it's end-to-end optimized software stack. And this particular ones we deployed, not only get the first, we actually deploy this on AWS marketplace, so which is AWS Cloud. You can check this out in AWS marketplace, AWS marketplace. And this technology we use is AWS Cloud AMI, which is basically for AWS particular container technique. And we also support Obtainer for on-premise system. And this part is not part of the thing we released for AWS, but this one we will release it for on-premise system like a Frontera or some other tech systems. And by the way, different system, at least right now, different systems, they support different container. Like, what's that? For Microsoft Azure, it's used Singularity, okay? And for each of them, they're slightly different, so we have to customize this for each of them. Our goal is to support the end user to be cross different platform, the same thing. I mean, as far as if you use our package, okay, you don't have to change your code. And the package itself is support AI, all right? So this package itself supports all the AI models defined in either PyTorch or through Hugging Face, okay? And examples, we actually have examples in our release, supported in the release. It's Llama 3, OLM, basically it's open large language model, okay? And Picera as well as BERT. Some of the examples I will show. Okay. And we also support vision models, including the famous ResNet and other like UNet and stable diffusion, etc. And the key thing here, at least for now, we're not emphasize the performance benefit yet, okay? But I will show you performance benefit. The key thing here is user-friendly. It's out of box, because setting up an environment to run AI applications is a painful job. Okay, so here the key thing is we want to emphasize is out-of-box optimized solution. And basically we're supporting CPUs including x86 as well as ARM, and GPUs including NVIDIA, AMD as well as Intel, and interconnects. And for AWS, it's EFA, okay? But our solutions will be applicable to others as well, including InfiniBand, Rocky, Slingshot, and this kind. Okay, so the package itself, we just highlighted, it's a distributed PyTorch. For this particular example, it's a distributed PyTorch example models, which actually use ResNet 50. It's more like a benchmark for all the AI packages, and see how it's performed. And this particular task or benchmark we're taking is ResNet 50. I think we use ImageNet itself. Okay. Is that right? Sometimes we're using synthetic. I don't think it's showing here. And this one is, again, showing the evaluation is done on Frontera, which is on-premise system. And it's using NVIDIA RTX module. Basically, it's 4 GPUs packed together for a single node. And the interconnect, and there is HDR, 100 gigabits per second, InfiniBand. As you can see here, we're showing the performance benefit. And as the number of GPUs increases, because here, if you show, this one is 4 GPUs per node. So the maximum here we're showing are 2 nodes. It's 2 nodes here. And as you can see, the benefit actually is more for single node, okay? Then for cross node, you suffer a little bit, but still noticeable benefit, more than close to 300%. And this example is a BERT. That's a large language model out of Google. Okay, actually, this is one of the early large language models. And this particular task is done on AWS G4DN instance. By the way, G4DN itself has many sub-instance types, okay? And for this particular one, I think it's on 16x large. That, you mean G4D dot 16x large. And so here we're using NVIDIA T4, which is a Tesla T4 type. It's a relatively older technology from NVIDIA, but that's what is provided on that instance type from AWS. The interconnect is AWS, it's an EFA, which is 50 gigabits per second. This is one of the slower interconnect. As you can see here, we are also seeing noticeable speed up. Okay, so the minimum we show is what, 40% performance benefit. And I want to emphasize again, this package, most focus is for user-friendly deployment. Okay, and even for that, once you start using it, you'll see the benefit, performance benefit. Okay. And last one, I'm just showing, I think some of you already showed this result, okay? So this is for parallel inference, not just for training. And this is a part of a package. And the research done, this part of the research is done on OSU side, but we are able to incorporate it as a product to provide commercial support, okay? And so this is doing parallel inference. This is the number of requests. The queue is cut off. Okay, number of requests. Okay, as you can see, the more requests we are request to process demanded by the end user, will still the significant more benefit. And so around 10x or higher, 10 times or higher, okay? The main thing there is because we're able to overlap the performance processing needed between computation and communication among different requests. So we're overlapping them, pipelining and parallel processing. This is what this package is able to achieve. Okay, so conclusion. As a company, we offer a suite of software middleware, okay, for accelerating HPC as well as AI applications with a focus on efficient communication, overlapping between communication and computation, as well as providing solutions for security in communication. Okay. Of course, right now we have different products for this. If there is need, we will be able to incorporate them together according to your needs. If you need secured AI package, we potentially can work on that. But right now, it's a separate product. We provided innovative, value-added product and emphasize on scalability for performance. And we're exploring the overlap and parallelism between DPU, CPU, and GPU, or whatever other units. If you need some special support, we potentially can work with you. And here we demonstrate the different approaches to accelerate basically for AI application as well as HPC application. HPC we emphasize is MPI-based HPC application. And after all, we will be very happy to engage with you as either end user or collaborators that to help you to find appropriate solutions for your own business. And I believe that's all. Thank you very much for your patience.
Any questions? Yes, Dr. Park.
Thank you for your presentation. Can I use the multiple packages in one applications? Is there any conflict from each other? For example, I'd like to training the BERT model using X-ScaleAI and X-ScaleSecureMPI.
That's the question. That's a good question, actually. Right now, we're providing separate products. And if you need a secured communication for your X-ScaleAI package, we need to work on that so we incorporate them. Right now, no. Yeah. Yes, go ahead.
So at the beginning of your presentation, you showed some result on using the DPUs.
Just a moment. Which slide are you referring to?
And yeah, any of those slides about the DPU usage.
Beginning.
My question is whether you have done any investigation or the experiment on using or just dedicating a number of cores within the same CPU for the
you mean
MPI
multi-rail
communication, so that essentially you can internally offload to some of those cores, right? Instead of offloading the MPI stack to the DPU, which is the outside of the CPU core.
Yeah.
Because in these days, the CPU tends to have a quite number of cores. So you can separate out, I don't know how many, 4, 8, 6, number of CPU cores and dedicate them for the MPI communication, just like you offload to the DPU. I think that should be quite interesting if you have such comparison.
That's a good point. And right now, the DPU is deployed not by us, okay, by NVIDIA. That's a system connection. So that one itself is attached to PCIe interface, okay. It's a single DPU unit. Now, by separate port, I guess you mean you have dedicated hardware connection to that DPU unit or something, that you can have multiple DPUs?
No, I don't think
I can answer. I think Dr. Han is suggesting instead of like offloading to DPU cores, in let's say one server has 128 cores, can I actually reserve 8 cores to carry out this kind of functionality?
Oh, okay.
Yes, the design is possible. In fact, from the MVAPICH project on the OSU side, we have done research on that. There is a paper several years back, but we never brought that design into the MVAPICH, but it can be done.
Yeah.
The trade-off will be based on the network adapter and the speed of the memory speed and all on that. But you can do, we had a paper, we do a search called golf or something, I remember. I can send you the pointer. We did study kind of things on that.
So basically that will allow you not to take an extra accelerator off the CPU, rather than use some of the cores, spare cores on the CPU to do this.
Assuming you have enough number of cores.
Yes.
So
Yeah.
when we build a new system, it's a trade-off between separate out or dedicating a few cores for the communications, or
Yeah,
buy another part, the DPU. I mean, it adds a cost to the system to
Yeah.
buy its number of cores to offload the entire MPI stack.
Yeah.
That one. So there's a trade-off.
yeah, that's true.
So the broad idea is that, I mean, if you, on any machines, if you look to an application person, he or she wants to use all the cores, right? Always, they don't want to leave any cores. But if you put a restriction, then it is okay. I think a lot of cloud providers provide that, and they dedicate some, like Azure, if you go, on every node, you will not get all the cores. So they have reserved actually some cores, they don't give it to the users. But as of now, they are carrying out more virtualization functionalities, not like offload. But similar designs can be done. If you totally restrict, saying out of 128 cores, the user will only get 120 cores, yes, this kind of designs can be done. But then you lose that 8 cores for all applications.
It's going to be very interesting to be able to see this.
It's an interesting trade-off, yeah, to be considered. But consider this. So
we break. Sorry for interrupting. I think
we can discuss.
Yeah, let's discuss offline because we are already eating into the break time. Let's thank Donglai.
Thank you.
Yeah. There was one question. Might be you answer. I think there was an.
Does extra Ethernet offer similar capabilities to SecureMPI? Yes, in the sense that we can support the Ethernet as well as the RACI. But right now, we have not evaluated the performance benefit for that yet. So we need, if you are interested, please contact us. We can work that out and see whether that fit your requirement.
No, I think the question is, does offer same as security? I think not.
Oh, no, that's not. I was thinking using the Ethernet to do the communication. Offer similar capability. So that means the security done.
You can talk to him offline.
Yeah, let me
Okay,
talk to the,
let's go for the break, and we'll have a 15 minutes break. Then we have the last session. We'll come back at break.